Hello, I'll be presenting a vehicle license plate detection system that I based on the SIFT algorithm. This work is to satisfy a requirement of final project of ECE 588 robot vision class, University of Michigan, Dearborn, summer of 2017. I'll start with a very quick overview of SIFT. SIFT stands for Scale Invariant Feature Transform. This is an algorithm proposed by Professor David Lowe from British Columbia University in Canada. It makes use of space scale and difference of Gaussian to come up with potential key points. It applies local search to find the extremes of the points and keep them. Then it drops the low resolution points and the points that are part of an edge. Basically, we want to keep only the corner points. For the remaining points, we try to find the orientation of these points. We look for the gradients of the points around this feature point, and we create a histogram of the gradients. In this case, most of the points will point to the left, so we will take this orientation and assign it to this feature point. We'll also take the ones that are 80% or above of the main one and also assign to this feature point. So this one will have three different orientations. Next, we'll look for a 16 by 16 area around the feature point, divided to 4 by 4 squares, and again look for the gradients of the points in each square and create a histogram out of that. This is how the histogram looks like. The arrow points to the direction, and the length of the arrow points to how many points were in this direction for each square. At the end of this point, we'll have 128 different points, and this will make up the descriptor of this feature point. So these are 3 different points, and the descriptor will look like something like that. Okay, this concludes the first part. The second part is the matching part. Matching means looks for the lowest distance between 2 points, and one of the more common ones is the L2, least mean square. Basically, this is a 2-dimensional representation of this approach. The distance between this point, red one, and the 2 points is given by this equation: square root of the the squares of the differences in the coordinates, so x coordinates and y coordinates. In our case, we have 128 coordinates. We'll have 128 of these squares. Okay. After the matching, we'll be looking for search algorithms. So the searches, there are again many ways for searching. 2 of the more common ones is the brute force and the approximate approach. Brute force means that you look for each point in one image and try to match it to all the point in our other image. So searching for the lowest distance in all the points in another image. This, of course, is time consuming and resource intensive. You'll create many hits, but many of them are fake hits, so it's not really very good. An approximate nearest neighbor search is much faster because it gives you only approximate distances, but they're good enough. David Lowe proposed a method for that called best benefit BBF, and the OpenCV implementation of the BBF is through the FLAN fast library for approximate nearest. This will be used in my program. Okay, so how does the BBF look like? So you have 2 images, and the first image you have a feature point, blue, and we did the match. We found that 3 points. The one has the best match, smallest distance. Again, distance is based on 128 dimensions, not 2 dimensions. Okay, but also found 2 potential matches. We try to eliminate the ones that are fake. We do this by getting the ratio of the best match distance to the other ones. If it's 80% or above, this is a strong indication that the second best match is a mirage, is a fake match, so it's eliminated. The ones that's less than 80% are kept. Experimental data show that this approach by itself eliminates 90% of the bad or fake matches, while at the same time it eliminates 5% of the good matches. It's a very good trade-off, basically. The other one is to speed up the process. We stop at 200 matches. We found between 1 and 200. We found a good match. We stop there. We don't go all the feature points on the other image. Okay, so now for the code, I used OpenCV 3.2.0 with Visual Studio 2015, C++ of course. I had to download the libraries and actually the source code and create the libraries. And I did lots of borrowing from open source code, but I did lots of changes also because of the changes in 3.1 above. The complete list of the sources I used provided. Okay, now let's jump to the code. So I loaded this program to the Visual Studio 2015. This program does many things. Based on the first switch, it will either show the feature points in an image, or it will show the match between two images. The second one will select whether I want to use brute force for match for searching, or I want to use plan. The third one I'm going to keep to 0 because it will switch between SIFT and SIRFT. It really does too, but we'll all discuss SIFT in this case. So first we'll start by loading the images, and then if the detection method is 0, which is a SIFT, we find the key points, and then we calculate the descriptors, and then present or print out how many feature points we found. Okay, if it's this is we don't care. Okay, this one, if we select 0, which means that we will be using brute force, then the matcher will be set to brute force, and we will get all the points through this matcher.match, and then provide the parameters to this function, and then print them out. If we are using flan, we need to specify the minimum distance we accept, which is in this case 250. Anything above 250 times 2 really will be rejected. Anything below less than that will be accepted as good match, and we print. Okay, for this one, if you only want to show the feature points. Okay, so let's have a program. I forgot to mention this first part is just to show the feature points in two images. Okay, so this is an image, and it's really the same image, but this one is tilted a little bit. And look at the feature points. Feature points are represented by circles. The circle size has a meaning. The bigger the circle size means that this feature point was discovered at a later stage of the program, because it's related to the sigma used in the Gaussian filter. Bigger sigma means bigger circle. And the direction is presented by the line. So this one has this direction, this feature point, and this feature one has this direction, and so on. Some feature points has more than one direction, and let me see if I can find one. Okay, so look at this one. This has two directions. Talked about 80%. So this feature point has two directions. So generally speaking, this feature, this image and its tilted version, they have very similar feature points discovered, which is a good thing really. We really want that, we expect that. Okay, so now let's try to do some matching. We change the values to, okay, so we're not showing here, we're gonna match. Let's start first with the brute force. And look at this, so many matches, but some of them are really in bad quality. Okay, so let's try the flan. Again, the same image and it's tilt. Okay, so the flan found 14 points. Let's look at them. Okay, much better. These are really good matches. 14 is really on the lower side. So the visual classification problem can be shown at different approaches. Basically, there is one recognition. Basically, you want to recognize that in an image that this is a bicycle, and this is a bike, and this is a car. Another way or another approach is categorization. You want to put all the moving vehicles under vehicles, like so it will be motorcycles and cars will be under the same class, where trees will be a different class, for example. For detection, you want to look for an element in an image. So give me all the trees, or give me all the flowers in the image, or the motorcycle, or something like that is detection. Content-based image retrieval is based on finding the feature points in an image and then using a classification technique for matching and classifying all the stuff. So some of the more common training and classification techniques are naive Bayes and the bag of features, or which is basically a bag of words. This is what will be used in our program. Okay. So I collected many pictures from online of different lesson plates, and I also got some donation from expired lesson plates from my neighbors and friends. And I took pictures, different scales, different dimensions, different orientations of these lesson plates, and I came up with 260 something images, different size, different orientation, everything. And this is what I use them. I divide them to different levels. One of them for clustering, the second one for training, and the third one for testing. And they are mixed, so some of the clustering will also show in the testing, and some of the testing will also show in the training, and so on. But for most the cases, most of the stuff are not repeated. Okay. The bag of features, which is based on the bag of words. This is a good implementation of this one. So this one shows you take different shoes, and you take the feature of each shoe, and you create a pool of all these feature points of all the different shoes. You take these and try to put them into clusters. Okay. So in this case, this feature point will fall in this cluster, this feature point in this cluster, maybe this and this maybe will fall in this cluster, and so on. After that, you try to solidify these clusters, and we'll talk about that later on. So this is the first stage of the this is called clustering. Next, you take images for training. So in this case, they take running shoes with laces, and then again extract the feature points, and then they match them to the cluster that was created from the previous one. Out of this, you create a histogram. So this training point will have this histogram. Basically, the histogram is created this like this. So and so of these feature points fall into this cluster, so that will have this level, and 10 of this feature will be under this cluster. So this has histogram like this. So this will be a signature of this training point. You take many training points and create many of these histograms. This will be your vocabulary really for training. You take this one and you apply the SVM, which will be discussed later on, and you get results. Okay, so this is another diagram. So you take the feature points, extract them, you create the dictionary through the bag of words or bag of features, and then you create the histograms. These are the training histograms, and then you apply the SVM, which is the support vector machine for classification. Support vector machine really provides a solution to the clustering problem. Basically, it's really the optimal solution, which means that the boundaries created through the SVM are the optimal boundaries that has equidistance between the different adjacent clusters. So SVM is used as solution to your clustering problem. Okay, back to the code. So I loaded the second program to Visual Studio, and this program does many things. First, it starts based on a switch. It will either build a dictionary, create a bag of words training set, or it will, if it's 3, it will train the SVM, or if it's 4, it will do the prediction. Okay, so if we set to 1, it will look for predicted dictionary, and I guess should run the program with one and see how it looks like. Okay, so this one is loading the images from the clustering folder that I provided. Different images for different states basically, and for each one you look at the feature points on each one. So this one takes a long time, so I'm gonna stop the program here and show you the results. So that's the vocabulary file, how it looks like. I selected 200 cluster size for my experiment, and each one of them shows like 128, which remember the 128 descriptor points. This one is a resultant of having 50 clustering images trained with the program. Okay, so next we will select next stage, which is basically training, and run. Okay, again this one is loading files from the training folder now, different folder, and doing the same thing, basically find the SIFT and then creating the histogram for each of these points to create a training set. Okay, again this one takes time, so I'm gonna stop it here and show you the results. Okay, so the file that contains the histogram has 50 because I have 50 training images, and it has 200 because I selected 200 clusters, and these values represent the histograms of all the 50 images. Okay, let's move to the next step. I'll set 1, 2, 3 to do the SVM and run. This one really doesn't take much time. Okay, so this is work, and I'll show you the results. Okay, so this step creates two files. The first file shows the format used or the settings used for the SVM, like C underscore SVC and RBF, all this stuff. It shows also the 200 again, the number of clusters. It shows two classes because I have Michigan plate or non-Michigan plate, and these are the values. And in addition, there is a label. So I used again 50 images for training, and if it's a 0, this means non-Michigan. If it's a 1, it's a Michigan. So we have exactly 25 non-Michigan and 25 Michigan plates in this training set. Okay, let's move to the last stage, which is the good one, the training, the testing, sorry. Okay, so the testing folder is a different folder, and run. It will use the results of the previous steps basically to test the whether this is a Michigan or non-Michigan. Again, it will be loading the place and will determine whether it's Michigan or non-Michigan. Takes a long time. We stop it and I show the results. Okay, so I loaded the results of the test images, about 50 images, 25, and found that the final prediction accuracy is about 89%. Not too bad, but we'll see why we have some misses. So these ones, they're missed. They're big. I'll show what big means. These are really big pictures, not part of the original training or clustering sets. And this one is not in the training set. It's not in the clustering set. This one, same thing, not in the clustering set. This one was not in the training set, but it was in the clustering set, but it still failed. So let's look at the images. So this is what I mean by big. This is not just the plate, but plate with the back of the car. So okay, this one failed. It's kind of blurry, maybe that's why. This one failed surprisingly. I don't know why. Could be, looks like maybe it's a drawing. And this one also failed. Okay, so let's try something else. Let's try to change. Remember we said 200 as the cluster size. Let's try to make it 500 now and see what happens. So we change this one to 500, and we'll run the same thing again and see what happens. and I'll basically jump to the results. So one more. Okay, so the results. Okay, not the right one. Okay, so changing the cluster size to 500 from 200 really made a big difference. Out of 255 images, many of them are big images, not just the small ones. The accuracy was 97.27%. This is a very good accuracy. Some of the failed ones, this could be a drawing. Tilted, I still should have discovered this one. These are big and side and tilted, and so there are more than one issue here. Big and sideways, big and tilted, and this one is bad. So basically, the increasing the cluster size from 200 to 500 made a big difference. Okay, so that concludes my presentation, and this is the references. Thanks for listening.